that there are 19 attendees. Thanks very much for coming and supporting the event. My name's Simon Arnold. I'm chairman of the Staffordshire Committee of the iMechE, and I'm very grateful this evening to Roger Sloman for giving us a talk on advanced blast and ballistic systems, and David Field is facilitating as well. And yeah, I see there's another attendee just joined, so hopefully more people will come in. So I'll go over to Roger Sloman, and Roger, please.
Yeah, I'm trying to get to share my screen, and it's not cooperating at the moment for some reason or another, because there's too many things up, and I'll just get rid of everything. I'll just get rid of everything. It's going to take forever. We might have to revert to you sharing it, I'm afraid, David.
No problem. So you just want your presentation up? Yep.
Well, hang on, I might have got rid of it. I might have got rid of it. Just let me check. It'd be better if I do it. I didn't realise I was going to use this laptop actually. So here we go. Got it. Right. Can you see it?
Not. Yeah. There we go.
Yeah.
Okay.
Sorry, Roger, I forgot to mention to the attendees that if you have any questions, please put them in the chat Q&A. It is available, so please place any questions in there or in the chat.
Right. Any problem is I can't make it. It won't give me slideshow.
Bottom. There you go. Bottom right.
Bottom right.
Next one.
Where bottom right?
Oh, right. Right. Again, one. There you go. That's it.
Okay, answer that. Okay. I need to go to it. Yeah. My apologies for that. We will get there very shortly. Okay. Okay. Thanks for everybody for attending, and without further ado, I'll get on with it. Yeah, this is what it's all about: protecting armoured vehicles from the effects of mine blast. And here you see the linear rocket motors that we use to do this, pushing down, just beginning to fire up as the mine blast has just gone off. This will be about five milliseconds into the event, and the motors are just beginning to fire up to push down on the vehicle. And that's a pretty amazing shot with the clarity that you get with it's probably 2000 frames per second, I think. Anyway, so it all began in April 2008 when I was blast tests on an armoured vehicle, which I can share that again. No, they don't want to let me. I'll go back one, and run it again so you can see it. That was the first time I'd ever organised a blast test and seen one. And when you look at the high-speed video, you can see that the mine goes off and the vehicle doesn't move for a certain period of time. So we see that again in the next slide. You see the shock wave from the deck cord leading to the mine, and the mine go over the vehicle within a millisecond or two, and the vehicle doesn't move at all. And when I asked the so-called experts in the company that I was working for, what the cause of the vehicle being blown into the air was, they all said, oh, it's the shockwave and reflected pressure, because that's a big peak in the force time curve. But clearly you see the, I'll try and show it again. It's slow in responding for some reason. See the shockwave pass over the vehicle, it definitely hasn't moved. So it cannot be that the shockwave and reflected pressure, which is a big peak in the force time curve, is actually lifting the vehicle. It's something else. And the obvious conclusion, it comes from the gas that's generated by the mine and the soil that's thrown up against the vehicle. So I thought, well, that 10 milliseconds is plenty of time to initiate some form of countermeasure. And when I looked at the NATO blast test standards at the time, this was already well known. The section here, I don't know if you can't see my cursor, can you? No, you can't, it's annoying. The section outlined in red, which is abstracted from that main text, says clearly that the shockwave hits the bottom within half a millisecond, suddenly causing extremely large peak, resulting in local acceleration of the bottom plate. Well, actually, it's not that causes the acceleration of the bottom plate. It's the gas and the ejector, but they didn't know that at the time, I don't think. And within 5 milliseconds, the bottom plate bends in both elastic and plastic regions. And yeah, all the damage is done in about 5 milliseconds. After that, the gas has gone effectively, and the ejectors stopped being projected. Well, haven't stopped being projected, but the main force has actually gone. So that's the damage to the vehicle. Then there's the global acceleration effects, the vehicle being thrown into the air. And again, this red outline abstract from the main text there, it's well recognized. It takes 10 to 20 milliseconds after the mine goes off before the complete vehicle begins to move. And that was, that was the observation I made. And I thought it was new, and it wasn't. It was well known. But nobody imagined you could do anything about it, obviously. So this is the sequence of events. Mine goes off, this damage done to the vehicle, this local structural response. Then the global vehicle response starts, the vehicle being thrown into the air at a high velocity, a very rapid acceleration from 0 to whatever velocity it gets to. And that can be 5, 10, 20, 40 meters per second even is possible. And that creates the occupant response, which is the G loadings on the occupants get so severe, you get spinal injuries, neck injuries, brain injuries, internal damage, and you bleed to death potentially. So it's not a very pleasant scenario, and it's a global acceleration. The vehicle's not penetrated, you still die, you can still die from the global acceleration or become severely injured. So understanding what happens is really key to working out what to do about it. So looking at the force time curve, you've got this initial large peak, which is the shockwave and reflected pressure that is talked about. And then you've got the forces generated by the gas from the mine and the ejector being thrown out from the soil. And you notice that it dribbles along above 0 for 20 milliseconds here. And in fact, that goes on for much, much longer, 200, 300 milliseconds at least. And that was something that wasn't really recognized when I started looking at this. And that contributes to the total impulse more than people thought. So the global acceleration effects are really important. They can kill you. Blast seats can only deal with 9 meters per second. This is a critical capability gap in terms of there's no ability to deal with it at the moment in any of the US or NATO armies, or globally indeed. And it's not just the acceleration upwards, crashing down on the ground is not pleasant either, and that can also severely injure or kill you. In terms of the operational utility, keeping the vehicle on its ground, on its wheels on the ground, makes recovery much easier, reducing exposure time for recovery crew, and weapons probably still be operational, so you can defend yourself. And this illustrates, this will run by itself. This illustrates just what can happen You've got a probably 15 to 20 ton vehicle there, and it's just thrown aside like a toy. It certainly wouldn't have done the occupants any good. I don't know what the outcome of that was, but it's a very good example of, thanks to the Taliban, showing what can happen. So the point is, it looks like there's nothing you can do about that, but we can make that vehicle weigh 500 tons or 1,000 tons, and it certainly would not be thrown in the air like that. And there is a potential solution, and that proposed solution is to push down on the vehicle with rocket motors. And this is the Vehicle Global Acceleration Mitigation, VGAM. And the original patent application, these are some of the drawings from it. You see, I show clusters of these motors on top corners of the vehicle, and this little novel rocket motor design, which turned out to be a circular form of the linear rocket motor that we've ended up with. So yeah, I invented the circular rocket motor. That's not very good. But anyway, the point is, it's quite a shallow bowl, very large exit area, because you've got to burn a lot of propellant very, very quickly and get all that gas out through the exit slots, and that's what it was designed to do. Okay, and that just illustrates, so you've got this time window for counteracting the global forces, and that's what you need to do. Thanks to Jankel for that. And force times time, so if you add up all the area under the curve, ever so simple, you get the impulse curve. And you know, contrary to what was said in that NATO standard, that the shockwave and reflected pressure drives the vehicle into the air, it doesn't. It's the total impulse that's transferred over a period of time. And interestingly, the 1 millisecond time scale, you only get 10 kilonewton seconds delivered. So, and it's only half completed, about 5 milliseconds. And this is another, it's a deeply buried mine, and you see the effect. There's no gas involved in that. It's just the road surface and the earth being thrown up. And this is similar to putting a mine in a culvert underneath a road. You get a very high impulse level generated by this big, massive earth hitting the vehicle. Not so much the gas in that case. So how do you generate huge forces required within 10 milliseconds? And there's only two ways of doing it. In principle, there's only one way. You've got to rapidly accelerate a mass to produce recoil or reaction forces. You could think of electromagnetic devices and rail guns and that kind of thing, but forget it. That's not practical for armoured vehicles. So there's only two ways: ballistic mass ejection. You explosively accelerate solid or liquid out of a tube or off a surface, or you use a rocket motor and generate gas ejected at high velocity. Impulse is mass time change in velocity. So velocity is very important in determining the efficiency of making the impulse. And such as a mortar, 160 meters per second probably, impulse per kilogram of mass is 0.16 kilonewton seconds. Rocket motor with the velocity of gas of 2,000 meters per second, you get 2 kilonewton seconds. So ratio is 12.5 times. So clearly rocket motors are the way to go. But ballistic mass ejection initially was simpler. We did experiment with it, and indeed Tenkate later adopted it for their system, which is the only competitive system to what we do. So we started by ejecting water from a small steel machined tube, kilo water, 42 grams of propellant. And when I measured this, astonishingly, I recorded about 36,000 kilos of thrust of load. You note that the motor is ignited by the deck cord entering the bottom of the pot. And we got some funding. The MOD did not believe that this could work, but they gave me 50,000 to demonstrate it. And this was the baseline test. You note the top of the containers is 5 meters above ground level. This is the baseline test. And that's the result of the baseline test. You still see the top of the container underneath the wheel of the vehicle. About 5 meter jump, centre of mass. And here you can see the setup with the 6 white painted ballistic mass ejection devices, and that's firing up the det cord. The sensors triggered the system at about 1/4 millisecond, lighting up the det cord to light up the motors. And I had 2 ways of doing it. One is reserve and just to make sure that it worked. And here you see the water coming out. And at that point, you've theoretically made that vehicle weigh 220 tons. And you'd expect it to stay on the ground. However, it didn't, because we've still got about 2 meter jump height. It's well reduced from 5 meters, so a 60% reduction. But we still got a jump. The exit velocity of that water, or its initial acceleration up the motors, I think must have been 2,000 meters per second to give 12 kilonewton seconds to produce that observed effect. But the point is that it still jumped. And the reason is that when you deliver all the impulse instantaneously at the start, you miss the impulse curve that follows. That's the rationale for that. So there's more to learn from just looking at stills of the baseline test here. Here you see the debts going off here, the little purple patch underneath the vehicle. 1 millisecond, the det cord's igniting. Possibly the mine's gone off, who knows. Some ejector. Now, if I just run that back the other way, you can see the intersection of the red and the silver on the column in the center of the vehicle. If you watch that, it starts moving at 2-3 milliseconds. And in fact, if you also look at the rear end of the vehicle, the red beams, you see they flip down. So clearly the vehicle is bending in the middle, but if you look at the rear wheel, you can still see that the ejector is just coming around the edges of the wheel. It's not going under the wheel. The wheel is still on the ground. So it's really quite interesting observation. You can see that 6 milliseconds, the gas ejector has got to the end of the vehicle. The damage process is complete. Vehicle still on the ground. That's really quite interesting. So the observations from that takes 5 milliseconds to get to the end of the vehicle, so about 1 meter per millisecond. The gas cloud expands, center of the vehicle moves up, bends, and we now know the gas cloud expansion rate, so we can calculate the quasi-static gas pressure acting on the vehicle belly plate underneath the vehicle, and we do that by I'm not a mathematician, I hasten to add, so I do it very simply by taking 1 millisecond steps, do a simplistic analysis of the quasi-static gas pressure underneath the vehicle, and you see it drops very rapidly from 500 psi at 1 millisecond to 127 at 2, 56 at 3, right the way down to 10 psi at 7 milliseconds. So really it's all done pretty much in 4 or 5 milliseconds. So 80% is done in 5 milliseconds. And you can calculate the impulse and you get to a total of 13 kilonewton seconds. So that's quite interesting. And when you think what the primary cause of the acceleration is, you've got the jig weight, the jump height, the initial velocity to get to that height, 5 meters for the impulse, and contribution of the gas. 65% of the contribution to impulse is from the gas, just the quasi-static pressure of the gas. And when I ran that past people, I used to run this past people that I visited, like British Aerospace Systems, GDLS, Renault, the TNO research organisation in Holland, and I asked them what their view was of the ratio of the effect. They came up with 60% for the gas as well, so that was quite pleasing. So there's a frequent perception that holding the vehicle down against a blast will result in more damage. Complete load of rubbish. And the evidence from the two tests, the baseline and the VGAM one, there's very little difference between the deformation of the belly plate in those two. And in fact, there was a split in the baseline one. There was only 3 mm steel on the sandwich section that I used underneath, whereas the VGAM one has just got a tiny crack. So that was quite interesting that it worked like that. And the other thing is the honeycomb within the sandwich structure, directly above the mine, it's completely crushed. A foot away, it's not crushed at all, illustrating beautifully that with a flat anti-tank mine, you get 2 columns of gas, high velocity gas, going vertically in opposite directions. And you think about the impulse that's generating, 3 kilos going up, 2,000 meters per second, 6 kilonewton seconds. Due to the dynamic effect, add a bit of soil and gives you 10 kilonewton seconds in total, which happens to be what the Ellis Dyna analysis said as well. So that's simple logic. Whether it's right or not, I'm not quite sure, but it seems to be. And the gas going down and digs the crater out, so high pressure gas comes out. So adding the quasi-static gas pressure, quasi-static impulse, so you get 23 kilonewton seconds, which is what was required to push that vehicle 5 meters in the air. So why is no more damage done to holding down? Because it's all caused within 5 milliseconds. The vehicle doesn't move for 10, so clearly it's not going to do any more damage. And that was army people who suggested it might do more damage quite frequently. So we did then look at large scale ballistic mass ejection. We ended up with 120 kilos of mass being ejected from a foot diameter tube at 90 meters per second, giving nearly 11 kilonewton seconds worth of impulse. It's worth just looking at how we did that. So there's another patent application went in using a column to bridge between the roof and the floor, put motors inside there, and then you're pushing down on the floor as well, which stabilizes the floor against the mine blast. So I came up with various designs incorporating both the ballistic mass ejection and the rocket motor within the column. That would all work beautifully in principle, and that would allow you to get away from the horrible V-shaped holes. And when I drew that first thing on the left, I thought I'd made the angle too steep, and then the foxhound next door to it was even steeper. And if you have a column in the middle to push down, you could make it a lot flatter, a lot more central, and a lot more room inside. And that's just repeating the same thing really. And I came up with designs where you could put you see the exit holes of columns in the roof of the vehicle. So you could put tubes down to the belly plate, going through down to the belly plate or the floor or the secondary floor, and have side doors. But lo and behold, well, yeah, so there's all these fundamental potential advantages that you could think of. Unfortunately, the military do not like the tubes going through the vehicles. They do not like side doors because when you draw up to dismount your troops, you face the enemy. And side-mounted doors are not a good idea, apparently. So you want a rear door. And furthermore, they don't like explosive devices in the vehicle, even though they carry a lot of explosive devices. So there's lots of reasons why they didn't like this. Nevertheless, I mean, we did do quite a lot of work on it. And here we built a 3-ton trolley on rails. And the porta cabin was designed to stop the noise from annoying the neighbours. this, oh, unfortunately, I can't make that play. That's a, oh, it did play. I'll go back and see if we could run that again. Don't watch the trolley, watch the porter cabin. Watch the end of the porter cabin. Right, now I don't know if you saw that, but the porter cabin actually jumped back 3 inches. And this is a 40-foot container on the ground. It's not on rails. It actually jumped back 3 inches. And after 3 or 4 tests, the walls were suffering, being blown out, and the EFP type device that we were kicking out of the tube was going straight through the wooden sleepers at the back end of the porter cabin. So we thought we'd better bury it. So we buried it and continued testing, and I don't know again if this will play. Yeah, it will. So that's 6 kilonewton seconds being generated, and that's 10.5, and you blink and you miss it. I think I might have a slow motion version of that. Yeah, you just about see it start to move. So we did quite a lot of work on it, and we did get some more funding from the MOD in the UK, do a series of tests. And so here we've got one big tube in the middle to deal with the main blast, and then 6 smaller tubes around the outside to deal with the longer duration delivery of the impulse from the mine. And that was all set up, all agreed with the MOD guy, DSDL, who was overseeing the project. And when we got to the range, he said, actually, I want you to fire them all off at once rather than in sequence, which was a bit of a pity. However, we did that, and what happened, we actually blew the belly plate off the test rig, completely blew it off. But it was interesting information in that the velocity required by the jig when the motors were not active, immediately it starts to move. When we've got the motors active, you see the movement is delayed for 3.5 milliseconds, but then the belly plate that's been blown off comes back up, collects the top part of the jig, and it reaches the same velocity, exactly the same velocity as the one without the motors firing. So it was really quite an interesting thing, and it was actually as a result of that I decided that we needed to put the linear rocket motors on the belly plate. One of the options was to blow the belly plate off to protect the vehicle, squash the blast effectively. And this suggested that you needed the rocket motors to be fired for a period of time. So that was one element of the patent application I put in. I decided, though, while we were down there, we had these motors on this test tube. We'd take an old Land Rover Discovery, stick the big motor in the middle with a belly plate underneath it, very simple belly plate, 15 mm mild steel, put a tube in it, see what happens. And lo and behold, we got a really impressive result in that that's had 6 kilos under it. It's completely standard apart from the ballistic mass ejection tube and the belly plate. And you see there's very little damage. The belly plate is distorted a little. The glass is broken in the vehicle, and very little floor deformation. And that's really quite an impressive result for such a crude test. Still didn't convince anybody to put tube in their vehicle, however. So it was efficient. It's heavy, and there's no room in the vehicle for explosive devices. Don't like them inside the vehicle. So, but there were other concepts that were very similar, and the hardwire structural blast chimney is another slightly dumb answer to the problem. It's an open tube through the vehicle to relieve the blast gas pressure, and you see drawing here, which is all very well, but that's fine if the mine happens to be directly underneath the hole, and really it's really not going to take too high a percentage of the gas that's generated out. The vast majority is still going to go out the sides of the vehicle and create impulse driving the vehicle. Even so, even more silly people in Lockheed Martin came up with this design to patent, which was an even larger collection funnel, which would trap the gas for even longer and create even more impulse while it's trying to struggle out through the narrow tube. Utterly crazy, but there you go. That's what you get sometimes. And then, of course, there's the V-hull, and that was a horrible piece of design, but incredibly low ground clearance. But one of the issues with the V-hulls is that if the mine is off centre line, it's great if it's off right under the middle. If it's just inside the wheel or under the wheel, you've got a nice flat area to react against the blast and to blow it sideways. So V-hulls work, but they're not terribly clever in some ways. And you do have the high ground clearance issue that raises the centre of mass, and you get rollovers quite often with MRAPs. So the proper system, rocket motor development, we initially used Martin Baker aircraft ejection seat motors. Blink and you miss it. I'll try and run that again so you can see. And what you see is the test tube being slammed upwards and then slammed down again, which would be the worst possible scenario if you're sitting on it. Would not be good. So just running through, the arrow indicates the position of the jig. And here you can see the jig quite clearly. Gets thrown up and then thrown down equally rapidly by the ejection seat motor. But the really interesting thing is that the rocket motor is now burnt out at 250 milliseconds. Look at the ejector still flying out of the hole, which is why I said that dribbling along the above zero goes on for a long time. That must continue for at least a quarter of a second, as is illustrated by that picture. So, yeah, interesting observation. It's all about observation. So the linear rocket motor, and that's a small version. You see the exit slots cut transversely to a square section tube. A novel design of rocket motor, some 3,000 years after the Chinese invented them. Nice picture there. We've never got a better one than that, of the shock cones coming out from the motor, indicating high velocity exit. And that's just information on the motors. Currently, we're getting up to probably 9 kilonewton seconds from the motors. And the interesting thing is you're burning, you got 5 kilos of propellant. You're burning it at the rate of 400 kilos a second per motor. So use 8 motors, you're burning at the rate of 3.2 tons per second. So it is not surprising that you get a lot of impulse. Okay, and that's just the force time curve and the impulse curve. So, and one of the early tests on a snatch Lando, we just put a single motor on the back end with a couple of kilos underneath. And interesting observation that you see the rocket motors finish firing and the afterburn from the mine is still burning furiously. It's quite interesting. So the belly plate development. Using carbon fibre beams to spread the load from where the mine is underneath the vehicle to reduce the deformation. And this is a very heavy design designed for 12 kilos, just to see what we could do. It's not optimized though in any way. That was 12 kilos at 300mm standoff, and we got this 80mm of deformation from that. So that could certainly take more, possibly up to 20 kilos, certainly 15, probably 20 kilos. And what we're trying to demonstrate is that you could design a belly plate for a vehicle structure that could take 20 kilos. And if you push down on it with the motors, you can keep it on the ground as well. So we then did a more practical test on the Snatch Land Rover, 6 kilos, 2 motors, and there was an active floor system as well. And the result of this, mine goes off, motors fire, and the vehicle stays on the ground. And hopefully this will play. Yes, it does. This is the comparison without any motors. Pretty dire, goes about 6 meters in the air, splits the vehicle in half, and the end result is that everybody would have died pretty much. And you note that the belly plate is very badly deformed. That's a key issue. So this is the one after the 6 kilo active system test. No deformation in the vehicle at all. The belly plate took it all, and the vehicle stayed essentially on the ground. We just put a 30mm dent in the belly plate, and the device we had in the driver's seat showed there was no injury. That the threshold for injury, you can just see, is 17.7 on that index. So that was very satisfactory. And when we did the second blast test on it without the rocket motors firing, it got a jump height of only about 1.2 meters, which not the 5 meters that we saw from the previous baseline test, the earlier baseline test. So quite surprised about that. And we think that the flat belly plate staying flat enabled the gas to get away quickly from underneath the vehicle, reducing the impulse transfer. So we think that's an interesting observation, which we will continue to investigate. And that's it after 2 6 kilo mines underneath it, still intact, still undeformed, just bits of damage to the body. And we had a hybrid 3 dummy in which you have to demonstrate whether there's any injuries to the occupants. And this was sat in a Jankel blast seat, and all the numbers are way below the threshold, including the tibia numbers at the bottom. We had the dummy's feet on the floor, which is not normal. You don't do that, otherwise you break the dummy. We had an active floor system that pulled the floor down, or pushed the floor down when the mine went off, and that removed the floor from under the dummy's feet and saved it from injury. So we demonstrated really that it's pretty game changing. You can build a flat bottom vehicle, no V-hull, with 300mm ground clearance, capable of sustaining a 15, 20 kilo mine without significant deformation. It's pretty heavy and it's pretty sick, but you can do it. And you don't have to have any limb injuries due to floor shock. And you can eliminate the global acceleration using the LOMs, and that has been available to the industry for some time, if they cared to take any notice. So sensor control initiation system, you don't know what size of mine you're going to hit. It could be anything from anti-personnel mine to large IDs with very different force time curves as well. And you don't want to react in full to an anti-personnel mine or a small anti-vehicle or a decoy mine, because the first thing that people say is, oh, they'll set a decoy to set the system off and then another mine underneath to do the damage. Well, that is not really practical. Vehicles are usually traveling. You've got to be pretty clever to set a decoy that's going to work and do that. But we don't react to a low level. So the decoy almost certainly will not trigger our system. And the system deals with it. So it's because of the force time curve of the mine blast impulse transfer, you don't want to deliver all the impulse from the mine too quickly, or you'll miss it. You'll still get global acceleration. So the rocket motors do go on for a little bit longer. Sensing is interesting. We use pressure sensing to detect the shock wave, and we then measure the deformation of the belly plate. And I'm not going to say how we do that, but it's very simple. And then, you know, it can command either no fire, part fire, or full fire. So we have an adjustable response according to the size of the mine. And very importantly, there's no safety critical software involved in that process, because people just do not like safety critical software. So system hardware timing sequence, the shock is quartered half a millisecond, blast wave follows 1 millisecond. We sense the pressure within a millisecond, we sense the crush within 1.25. The system leaps into action, it arms, it runs in safe mode, so it cannot go off until we've received those two different sensor signals. So it's a completely safe system. It cannot go off accidentally. It can only go off if there is an explosion underneath the vehicle that causes sufficient deformation of the belly plate to kick the vehicle into the air. So it's a brilliant system, actually. It's very simple, and it does the job extremely well. And then you get the motors firing up a couple of milliseconds afterwards. So there is some discussion from certain places that you need an instant reaction within 1 millisecond. If you do, that is a ballistic element that you add to the system. It's not yet clear why you should need that. It doesn't quite stack up with our understanding of the blast event, the reaction of the vehicle and the blast seats, but there you go. Certain people do think that's true. And then you get the rocket motors to deal with the longer term impulse transfer. So a couple of normal designs, you can easily incorporate the linear rocket motors into a special forces vehicle concept. Tubes taking the force down to the floor to stop the floor being deformed. It's a very neat design. Sideways seat, so you can fire your weapons sideways. You get 9 guys on the vehicle, which was the American requirement for a squad vehicle. Again, nobody's picked up on it yet, but there you go, keep trying. And a civilian vehicle which would match any armored vehicle in its protection status, combining both ballistic protection and the VGAM system and active floor and everything else. You could do that way between 6 or 7 tons, but it can be done. And we thought that would work for heads of state and so on. Still, nobody's put their hands up yet on that one either. Keep working at it. So these are the systems: stop the global acceleration, stop floor shock injuries, stop the belly plate deforming and intruding into the cabin compartment, and you can have a high level of blast protection in a flat bottomed, no V, no ground clearance, civilian appearance design. So that is it. Bringing this up to date, we're developing belly plate to take 4 kilos under a Toyota Hilux, and we're pretty sure we can do 4 kilos, but we're doing a test on July the 15th to prove that. Lots of potential applications for that. Same design will also stop 6 kilos underbelly. Critically, the US Army has recognised the need to address the capability gap of excessive global acceleration with large IEDs. The Pentagon Rapid Reaction Technology Office has seen the BFPS video and contacted us directly, and the result of that is that there are proposals in to them, and we do expect to get significant funding from the US to develop this whole technology, really starting probably in October this year and the new fiscal year. So that's it. We have a crowdfunding round going on, so if anybody wants to help us save lives and stop people being disabled, that's the link for the pitch. And that's it. Thank you very much. So a few minutes to answer any questions that come up. I'll go back to that one so as you've got that review. Okay. Any questions, David? Well, there you go.
So there's one been posted in the Q&A, Roger. It said from Daz Wood, Roger, the VGAM test conducted on flattened bottom vehicles only, or did you conduct on V-bottom?
Yeah. Well, the answer is no, we haven't, because we're trying to demonstrate to people that the V is not essential. A V will help, a slight V will help, because you can. I mean, the reason is that it makes the belly plate structure both stiffer and stronger. It does divert the gas and the ejector from the mine as well, but that's a relatively minor benefit compared to the fact that it makes it stiffer and stronger. So that's the answer to that question. We haven't done that. We may do as things develop.
Okay, well, there's no more text questions. I'll take panelist advantage here and ask you with my voice, were any of the vehicles able to be driven? I know that there was the prop shaft space within the belly plate on one example photo or image.
Yes, no, I mean the on the snatch we didn't worry about that. Obviously, when you design something, it's like for the Toyota Hilux, yeah, that obviously has clearance for all the underbelly equipment. Yeah, so you leave space for the gearbox, prop shaft, exhaust, etc., and fuel tank. Yeah, it has to be practical, obviously. Yeah. And the belly plate for the Hilux, it's looking to weigh about 400 kilos, which is just about acceptable for that vehicle. You wouldn't want to both ballistically protect it and put the belly plate on, I suspect, but there are plenty of examples where you're exposed to mine blasts, legacy mines, but where there isn't any current ballistic threat. Not like the mine clearance operations, they don't go where there's any shooting. They make sure that where they are is safe and that it's only a mine threat. And there's a lot of people still being killed and injured by going over legacy mines that have moved. When you get floods and soft mud, these mines can move from off track to track, and accidents continue to happen.
Okay, so we've had another question in the text. Anonymous viewer asked, does the VGAM come with any routine maintenance requirements?
Very little indeed. There would be a routine replacement of the propellant, or the motor would be recycled to have the propellant replaced after a period of time, but that would initially, it might be something like 3 years or 5 years, but that would then extend probably to 8 or 10 over a period of time as the experience with the system. So yeah, the thing would be self-checking when you turn it on. It would check that all the circuits are intact and so on, that the sensors are working and so on. So very little routine maintenance. There would be a little bit on the sensors to make sure that they're still operational, like the pressure sensor. That could be a closed device, or it might be an open tube, but there's various different options on that. So yeah, very little maintenance really. So next question, you say for 6 kilo ID, if you can defend against that, won't they just double the kg? Yes, that's what they do, but it makes it more difficult for them. They've got to make more explosive, they've got to make a larger hole to bury it in. There's more risk of being detected. There's a lot of videos on YouTube of insurgents in Afghanistan, burying mines and being blown to pieces by TOW missiles fired from Apaches that are observing them with a sufficient standoff that they can't be heard. it's a dangerous game. You're planting IEDs, and quite often there's errors and they blow themselves up as well. So yeah, it's a valid point, and it just makes it more difficult. And yeah, you just have to go to a heavier vehicle if you want to defend against the larger charges. I'm afraid that's the nature of the game.
Yeah. No other questions as yet.
I mean, we can do at some point in future, we can do another update on all this. As I said, the US military have recognised they've got a problem they've got no solution for. Our solution is the only practically possible one with the rocket motors. You can't do it with ballistic mass ejection. Otherwise, it's massively heavy, massively inconvenient with all those mortars on the side of the vehicle. It simply doesn't work. So we have the only solution to it, and it's patented in America as well as globally. So we're in a really, really strong position to maximise return from that US recognition that they have a problem they can't deal with. And it's really gratifying after all these years, considering I started 13 years ago, and I've been pitching it to the Americans for 10 or 11. So yeah, it's gratifying, to say the least.
I bet it is. And of course, it's got to work first time every time, like the rocket motor to leave the moon had to work first time without doubt.
Yeah, it is highly reliable. The whole safe arm sensor initiation system is all highly reliable. It's exactly the same as used on air launched bombs, missiles, torpedoes, and so on in mind. So it's exactly the same type of system. So it's highly reliable, extremely safe, and we went for the very best ways of doing it from the start. So yeah, it's just about to come up to time. That was I didn't run through that through that presentation in the 117 slides or however many it is. I only finished it this afternoon, so that was good timing.
Yeah, it was another excellent presentation, Roger, of course, following the carbon fibre developments. I'm really grateful that you've been able to make these two presentations for us. It really helps the institution, the iMechE, to promote engineering to other people. And of course, that means having an excellent presentation and presenter to show us this interesting information. So thank you very much.
Yeah, no problem. We can do a good update on that in another year's time, I think. Okay.
Yeah.
All right, good stuff. Thanks for your time.
Thanks, everybody.